Simple harmonic motion. We're familiar with a simple pendulum swinging back and forth. If we introduce some terminology, we call the central position here the equilibrium position. The maximum displacement either side of the equilibrium position is called the amplitude. The time taken to do one complete oscillation, for instance from here to here and back to here, is called a time period, denoted by a capital T. Frequency, denoted by a lowercase f, is equal to the number of complete oscillations per second and is measured in hertz. Frequency is equal to 1 over the time period, which you can write as f is equal to 1 over t. When the pendulum is away from the equilibrium position, it experiences a force towards the equilibrium position. Let's see how. For this position of the pendulum here, the weight will act down. The tension will act along the string, and if this is angle theta, then this also will be angle theta, and there will be a component of the tension towards the center given by t sine theta. The greater the displacement, the greater the force will be. This force leads to an acceleration towards the center. So we can write a is equal to minus kx, where a is the acceleration, x the displacement, and k is a constant which depends on the particular setup of the pendulum. The minus sign tells us that the acceleration is in the opposite direction to the displacement. The acceleration is always towards the equilibrium position. So just writing again a equals minus kx, the bigger the constant k, the greater the acceleration will be for a particular displacement, and so the greater the frequency of the oscillation. It can be shown that the constant is equal to 2 pi f squared. So we get a is equal to minus 2 pi f squared times the displacement x. When the pendulum is at the maximum displacement from the equilibrium position, the restoring force is a maximum, and so the acceleration is a maximum. The velocity at this point will be 0. When the pendulum is at the equilibrium position, there is 0 restoring force, so 0 acceleration. But we have maximum velocity at this point. I'm now going to look at graphs of displacement, velocity, and acceleration against time for this pendulum. I've marked out the start time here at 0, time period over 4, half the time period, 3/4 the time period, and after one complete oscillation. These relate to the end positions and the equilibrium position of the pendulum as shown. I'll take the right hand side as positive and the left hand side as negative. I'll start here at t equals 0, and so I have maximum positive displacement, which I can mark here on my graph. At the moment, the velocity will be 0. The pendulum will be accelerating in this direction. This is the negative direction, and it will be a maximum acceleration in the negative direction. Here, at time period over 4, moving to the left, I now have 0 displacement. I have a maximum velocity in the negative direction, which will be down here, and I have 0 acceleration. Across here, now we are at half the time period, and we have now maximum displacement in the negative direction. We have 0 velocity, and we have maximum acceleration to the right in the positive direction. So I can mark here. coming across to the centre again at 3/4 the time period, moving to the right, we again have 0 displacement. We have maximum velocity in the positive direction and 0 acceleration. And finally, back here at the end of the time period, we again have maximum positive displacement, 0 velocity, and maximum negative acceleration. Now we can join these points with a line for displacement, for velocity, and for acceleration. Velocity is found from the gradient of a displacement against time graph, and you'll see here the displacement line has 0 gradient and we have 0 velocity. Here we have maximum negative gradient, and here maximum negative velocity, and so on. Acceleration is found from the gradient of a velocity time graph, and here we have maximum negative gradient and maximum negative acceleration. 0 gradient, 0 acceleration, and so on. It can be shown that displacement x is equal to a cos 2 pi ft. You won't be expected to derive this equation, but let's just have a look at it. It gives this cosine curve that we saw earlier for displacement against time. Now, also taking into account that frequency is equal to 1 over time period, we'll just look at a few points. When t equals 0 at this point, t here will equal 0, this term equals 0, and we end up with x is equal to a cos 0. As cosine of 0 is equal to 1, that gives us x is equal to a, so the displacement is the amplitude, which is what we have here. When the time is t over 4 at this point, we now have x is equal to a cos 2 pi, in place of f I've put 1 over t, times t over 4. This is simply 0, as is seen here. When t equals time period over 2, at this point, we get that x is equal to a cos 2 pi times 1 over t in place of frequency times the time period over 2. This gives us minus a, which we have here, minus the amplitude. At t equals 3 that times the time period over 4, at this point, we get x equals a cos 2 pi times 1 over t times 3t over 4, which comes out at 0 again. The maximum acceleration of a body in simple harmonic motion occurs when it has maximum displacement, and is given by this term. The maximum acceleration is equal to 2 pi f squared times the amplitude a. The velocity of the body at displacement x and amplitude a is given by this expression. The maximum velocity occurs when the displacement x is 0, and in this case the velocity will be given by plus or minus 2 pi f times the square root of a squared, which is simply a, giving this expression for the maximum velocity. You're not expected to derive any of these equations, and they are provided on the datasheet. The previous case was when the pendulum was starting at maximum displacement. If we take the start time at 0 displacement, we get a sine curve, like this. Just running through the maths of the different positions here, well, again remembering that the frequency is 1 over the time period, so we can substitute 1 over time period for frequency here. At t equals 0, we get x is equal to a sine 0. And the sine of 0 is 0, so x is just equal to 0, as we show here. When t is equal to time period over 4, at this position, we then get x is equal to a sine 2 pi times 1 over time period over 4. This simplifies to x is equal to a sine pi over 2, which comes out at 1, giving us x is equal to the amplitude a. Not forgetting, of course, to make sure your calculator is in radians. When the time is half the time period, at this point, we then get that x is equal to a sine 2 pi times 1 over t times t over 2. This becomes x is equal to a sine pi, and this again comes out at 0, as the sine of pi is 0. And finally, when the time is 3 times the time period over 4, here, we then get x is equal to a sine 2 pi times 1 over t times 3t over 4, which simplifies to x is equal to a sine 3 pi by 2. This comes out at minus a, so as we see we have minus the amplitude at this point. So, when the pendulum is starting at the midpoint, we use this expression, x is equal to a sine 2 pi ft. When the pendulum is starting at maximum displacement, we use the previous expression, x is equal to a cos 2 pi ft.